Have you ever imagined stepping into a world where creatures so bizarre and extraordinary roam the earth that they would make the wildest science fiction movies look ordinary? Picture this. Animals with necks so impossibly long they could peek into modern skyscrapers. Giants covered in armor that would make medieval knights jealous. And predators so massive they could swallow a small car whole. This isn't fantasy. This was reality. 170 million years ago, during one of the most incredible chapters in our planet's history. Welcome to the Mid Jurassic Period, a time when Earth was populated by some of the most unusual and mind-boggling dinosaurs that ever existed. We're talking about creatures that seem like they were designed by someone with an incredibly wild imagination. But here's the thing that'll blow your mind. These weren't just random evolutionary experiments. Every single bizarre feature, every strange adaptation, every seemingly impossible body part served a purpose that allowed these magnificent beasts to thrive in ways that still leave scientists scratching their heads today. I'm about to take you on a journey that will completely change how you think about dinosaurs. Forget everything you thought you knew about these ancient giants, because what I'm going to show you will reveal creatures so extraordinary that they challenge our understanding of what's even possible in the natural world. By the end of this exploration, you'll understand why the Mid-Jurassic Period produced some of the most successful and dominant life forms our planet has ever seen. But first, let me paint you a picture of just how different our world was back then. Imagine a planet where the very continents themselves were in motion, splitting apart in a geological dance that would reshape everything. The supercontinent Pangaea was breaking up, creating massive earthquakes that would make our strongest modern quakes look like gentle tremors. Mountain ranges were being born, oceans were forming where none existed before, and the climate was transforming in ways that would create perfect conditions for these incredible creatures to evolve. The temperature was dramatically different from today. While some areas experienced cooling and even ice formation, the oceans were warming up by about 8 degrees Celsius compared to modern temperatures. This created a world of lush tropical vegetation that stretched across vast distances. Imagine forests of giant ferns, cycads that looked like palm trees, and carnivorous woods filled with the ancestors of our modern pines and cypresses. This wasn't just a different world. It was a world that seemed designed specifically for giants. And speaking of giants, let's talk about the absolute masters of this ancient realm. The sauropods of the Mid-Jurassic weren't just big. They were incomprehensibly massive. We're talking about animals that stretched over 20 meters in length and weighed as much as 39 tons. To put that in perspective, that's like having 6 full-grown African elephants stacked on top of each other, then stretched out into one impossibly long creature. But here's where it gets really interesting. These weren't just scaled-up versions of smaller animals. Evolution had crafted something completely unique. Take Brachiosaurus, for example. This creature had front legs that were significantly longer than its back legs, creating a body shape unlike anything we see in the modern world. It was like nature decided to build a living skyscraper with legs. The neck alone contained vertebrae that looked like giant hockey pucks, creating a structure so long it could reach heights that modern giraffes can only dream of. Now, you might be wondering, why did these animals need to be so impossibly tall? The answer lies in the forests of their time. The mid-Jurassic world was filled with towering conifers and cycads that created a multi-story ecosystem. Different dinosaurs had evolved to feed at different levels, like living in a massive natural apartment building. The Brachiosaurus claimed the penthouse, feeding on the highest branches that no other creature could reach. But not every sauropod went for the extreme height strategy. Enter Cetiosaurus, a fascinating creature that took a completely different approach. These animals were still massive, reaching about 16 meters in length and weighing around 11 tons, but they had proportionally shorter necks and tails. Instead of reaching for the sky, they perfected the art of feeding in the middle stories of the forest. They were like the middle management of the dinosaur world, occupying a crucial ecological niche that kept the entire system balanced. What's absolutely mind-blowing is how these creatures managed their daily energy needs. A single Brachiosaurus needed to consume over half a ton of vegetation every single day. That's like eating an entire small tree's worth of leaves and shoots daily. Their teeth had evolved into precise cutting tools, working like giant scissors to strip branches bare of their nutritious content. Once they had exhausted the food in one area, these herds would migrate across vast distances, following seasonal patterns that took them across continents. This brings us to one of the most fascinating aspects of mid-Jurassic life, the incredible diversity of survival strategies. While the sauropods were perfecting the art of being gentle giants, other dinosaurs were developing completely different approaches to thriving in this ancient world. Consider the ornithopods, dinosaurs that were about a meter long, but possessed an adaptability that would make modern survivalists envious. These creatures had mastered the art of versatility. They could run swiftly on their hind legs when danger threatened, using their stiff tails as perfectly balanced rudders. But when it was time to feed, they would drop down to all fours, allowing them to graze efficiently on low-growing vegetation. Over time, these dinosaurs developed something truly remarkable. Their spines began to curve and adapt to their dual lifestyle, eventually creating a hump-like structure on their backs, similar to what we see in modern bison. This wasn't just a random evolutionary quirk. It was a brilliant engineering solution that allowed them to be both swift runners and efficient grazers. But perhaps the most incredible aspect of these ornithopods was their climbing ability. When threatened by ground-based predators, they could scramble up trees with an agility that would impress modern primates. Imagine a creature that could outrun a horse on flat ground, then immediately scale a tree like a giant squirrel when the situation demanded it. This kind of versatility was key to surviving in a world filled with massive predators. And speaking of predators, the mid-Jurassic period produced some of the most formidable hunting machines in Earth's history. Megalosaurus represents one of the most perfectly designed killing machines ever to walk our planet. standing up to 6 meters long and weighing around 700 kilograms. These predators moved on two powerful hind legs while maintaining perfect balance with their thick, muscular tails. What made Megalosaurus truly terrifying wasn't just their size, but their equipment. They possessed short but incredibly powerful forelimbs armed with razor-sharp claws, and their mouths were filled with long, knife-like teeth that could slice through flesh and bone with devastating efficiency. These weren't just big lizards with teeth. They were precision-engineered predators that had evolved every aspect of their anatomy for one purpose: taking down prey. But the Mid-Jurassic arms race didn't stop there. Scientists discovered evidence of an even more formidable predator, initially dubbed the Minden monster. When researchers found a rib that was 50% larger than those of Allosaurus, one of the most gigantic carnivorous dinosaurs known, they realized they were dealing with something unprecedented. Initial estimates suggested this creature could have been up to 15 meters long, making it one of the largest land predators ever discovered. The existence of such massive predators raises fascinating questions about the ecosystem dynamics of the Mid-Jurassic. How did these giant hunters find enough food to sustain themselves? What kinds of prey could possibly satisfy their enormous appetites? The answers reveal a world of constant drama and survival challenges that would make any nature documentary look tame. The herbivorous giants didn't just passively accept their role as potential prey. Evolution had equipped them with their own defensive strategies. The massive sauropods could use their powerful tails as devastating weapons, capable of breaking bones and sending even the largest predators flying. Their sheer size alone was often enough to deter attacks. But when threatened, a herd of angry sauropods could create a defensive formation that would be nearly impossible for any predator to penetrate. This constant evolutionary pressure between predators and prey created an environment where only the most innovative and adaptable species could survive. It was like an ongoing arms race, where each side had to constantly develop new strategies and capabilities to stay ahead of their opponents. But the Mid-Jurassic world wasn't limited to terrestrial giants. The skies above teemed with their own collection of unusual creatures. Pterosaurs dominated the aerial realm, and these weren't the massive flying reptiles that many people imagine from later periods. The Mid-Jurassic pterosaurs were smaller, more agile creatures with long tails and numerous sharp teeth that made them incredibly efficient hunters of insects and small vertebrates. These flying predators possessed wide wing membranes that connected to their hind legs, creating a flight surface that allowed for remarkable maneuverability. But perhaps most importantly, they had evolved strong claws that made them excellent climbers. This meant they could live in trees when not flying, giving them access to ecological niches that ground-based animals couldn't exploit. Yeah, what's particularly fascinating about these pterosaurs is their thermal regulation system. They possessed soft tissue crests on their heads that scientists believe helped them manage their body temperature, allowing them to remain active even during cooler periods that would have slowed down other reptiles. The aquatic environments of the mid-Jurassic were equally spectacular, filled with creatures that seem almost alien by modern standards. The warm seas supported an incredible diversity of marine life, including some of the most unusual reptiles ever to inhabit our oceans. Plesiosaurs ruled these ancient waters, and they came in two dramatically different forms that reveal the incredible creativity of evolutionary processes. The first type possessed necks so incredibly long that they would make modern giraffes weep with envy. These necks contained up to 76 vertebrae, each shaped like a hockey puck, creating a flexible feeding apparatus that allowed these creatures to hover in the water while picking off small prey that swam by. These long-necked plesiosaurs weren't built for speed or agility. Instead, they were the patient hunters of their time, using their enormous necks to reach into crevices and corners where smaller marine creatures tried to hide. They could remain motionless in the water for hours, their necks moving like giant underwater snakes as they searched for krill and other small organisms. The second type of plesiosaur took a completely opposite approach to marine domination. These creatures, also called pliosaurs, had short necks but massive heads and incredibly powerful bodies that could reach lengths of up to 17 meters. They were the orcas of their time, fast and agile predators that could pursue and capture large prey with devastating efficiency. What makes these marine reptiles even more remarkable is that they were warm-blooded, air-breathing creatures that gave birth to live young. This combination of characteristics allowed them to be active predators in ways that modern marine reptiles simply cannot match. The mid-Jurassic seas weren't just home to these massive marine reptiles. They supported an entire underwater ecosystem that would seem completely foreign to us today. Ancient crocodiles had taken to the oceans, evolving features that would make modern marine biologists do double takes. These weren't the stocky, heavy-bodied crocodiles we know today. Instead, they had developed long, narrow snouts packed with needle-sharp teeth that were perfectly designed for snatching fish from the water. Some of these marine crocodiles had gone even further in their aquatic adaptation. Evolution had transformed their legs into flippers and given them tail fins that allowed them to swim with incredible speed and efficiency. Imagine a crocodile that moved through the water like a dolphin, and you'll start to get a picture of just how bizarre and wonderful these creatures were. But here's what's truly mind-blowing about the mid-Jurassic marine environment. It was absolutely packed with arthropods. The warm waters supported massive populations of crustaceans that would eventually give rise to many of the creatures we find in our modern oceans. However, there's a fascinating twist to this story. All the crustaceans that we now associate with freshwater environments were actually living in salt water back then. It's like evolution decided to completely flip the script on where these creatures belonged. The diversity of life in these ancient seas extended far beyond reptiles and arthropods. Large sea turtles were making their debut during this period, adding yet another layer to the complex marine food web. These weren't just slightly different versions of modern sea turtles. They were entirely new experiments in turtle design, with features and capabilities that we're still trying to fully understand. What strikes me as absolutely incredible is how every single niche in this mid-Jurassic world was filled by some creature that had evolved specifically to exploit it. There were no empty ecological spaces, no unexploited resources. Every possible way of making a living had been discovered and perfected by some species. This brings us to one of the most fascinating groups of mid-Jurassic creatures, the early mammals. Now, when I say mammals, don't picture anything like the large mammals we know today. These were tiny creatures, most no bigger than modern shrews. But they were already showing the innovations that would eventually lead to the incredible diversity of mammalian life we see today. The cynodonts represent some of the most important transitional creatures in evolutionary history. These small animals, measuring just 10 to 20 centimeters in length, were developing features that would become crucial to mammalian success. They possessed specialized sensory whiskers called vibrissae, the same type of sensory equipment that modern cats and seals use to navigate their environments. But don't let their small size fool you into thinking these were harmless creatures. Many of them were skilled predators in their own right, hunting insects and other small animals with a precision that would impress any modern hunter. They had sharp teeth, perfectly designed for cracking hard seeds and nuts, and their fur provided insulation that allowed them to remain active during cooler periods when reptiles became sluggish. What's particularly remarkable about these early mammals is their activity patterns. While the giant dinosaurs dominated the daylight hours, the mammals had claimed the night shift. Their fur kept them warm in the cooler nighttime temperatures, and their enhanced senses allowed them to hunt effectively in complete darkness. This meant they could avoid most of the large predators while still finding plenty of food to sustain themselves. The evolutionary explosion of mammals during the mid-Jurassic period was happening at a rate that scientists are still trying to fully comprehend. Recent research suggests that mammalian evolution was proceeding 10 times faster during this period than it would in later eras. Something about the mid-Jurassic environment was creating perfect conditions for rapid evolutionary innovation. Scientists have proposed several theories for this evolutionary acceleration. The changing climate and fragmenting continents were creating new ecological niches at an unprecedented rate. The development of live birth, enhanced sensory capabilities, and improved predator avoidance strategies all contributed to mammalian success. But perhaps most importantly, their ability to remain active at night gave them access to resources and opportunities that other animals simply couldn't exploit. The insect world of the mid-Jurassic was equally fascinating and bizarre. The warm, humid climate supported enormous populations of flying insects that filled the skies with constant activity. Dragonflies with wingspans that would dwarf their modern descendants patrolled the airways, while beetles scuttled across the forest floor in search of decaying organic matter. But perhaps the most remarkable insects of this period were the ancient crickets. Scientists have actually managed to reconstruct the sounds these creatures made based on fossilized remains found in China. Using sophisticated acoustic analysis, researchers determined that male crickets from 170 million years ago produced pure musical tones at frequencies around 6.4 kilohertz. Imagine walking through a mid-Jurassic forest and hearing the same basic sound that crickets make today, connecting us across an almost incomprehensible span of time. The success of insect life during this period created the foundation for much of the terrestrial food web. These countless flying and crawling creatures provided food for the early mammals, the smaller dinosaurs, the pterosaurs, and countless other predators. Without this thriving insect community, the entire ecosystem would have collapsed. But what really sets the mid-Jurassic period apart is how all these different groups of animals had developed such intricate relationships with each other. The giant sauropods weren't just randomly wandering around eating plants. They were following migration routes that took them to different feeding areas throughout the year, probably covering thousands of miles in their constant search for fresh vegetation. These migrations would have created incredible spectacles. Imagine herds of 20-meter-long Brachiosaurus moving across the landscape like living mountains, their footsteps creating earthquakes that could be felt for miles around. The migration routes of these giants would have been like highways through the ancient world, creating pathways that other animals could follow and exploit. The predators of the mid-Jurassic had to be incredibly strategic in their hunting approaches. A creature like Megalosaurus couldn't just chase down any prey it wanted. These massive predators had to carefully select their targets, often focusing on younger or weaker individuals that they could successfully overcome without risking serious injury to themselves. The hunt scenarios that played out in the mid-Jurassic world would have been absolutely epic. Picture a massive Megalosaurus stalking a herd of Cetiosaurus near a river. The predator would have to approach carefully, using whatever cover was available to get close enough for a successful attack. But the herbivores weren't helpless victims. They had keen senses, powerful defensive weapons in their tails, and the protection that came from living in groups. When an attack did occur, the entire ecosystem would have felt the impact. The sounds of battle between multi-ton creatures would have echoed for miles, alerting every other animal in the area to the drama unfolding. Smaller creatures would have scattered to safety, while scavengers would have begun gathering in anticipation of the feast that might follow. The aftermath of such encounters would have provided opportunities for countless other species. Small mammals might have crept out to gnaw on abandoned bones, gaining crucial nutrients that they couldn't obtain anywhere else. Flying pterosaurs could have swooped in to grab scraps of flesh, while various insects and other invertebrates would have processed the organic matter in ways that enriched the soil for future plant growth. This constant cycle of life, death, and renewal created an ecosystem of incredible complexity and efficiency. Nothing was wasted in the mid-Jurassic world. Every death became an opportunity for life. Every failed hunt became a lesson in survival. And every successful adaptation became a template for future evolutionary innovations. The plant communities of this period were equally remarkable in their diversity and specialization. The forests weren't just random collections of trees and ferns. They were carefully structured communities where different plants had evolved to exploit different environmental conditions and resources. The tallest trees created a canopy that filtered sunlight and created distinct microclimates below. The middle story was dominated by different species that could thrive in the reduced light conditions, while the forest floor supported ferns and other low-growing plants that specialized in extremely low-light environments. This vertical stratification of plant communities created corresponding opportunities for animals. Each layer of the forest supported its own collection of creatures, from the giant sauropods feeding in the canopy to tiny mammals foraging on the forest floor. The complexity of these relationships was staggering, with each species depending on dozens of others for food, shelter, or other essential resources. The pollination strategies of mid-Jurassic plants reveal another layer of this complexity. Many plants had evolved to rely on wind pollination, producing enormous quantities of pollen that could travel vast distances to fertilize distant relatives. This strategy allowed plant species to maintain genetic diversity, even when individual populations were separated by hundreds of miles. Other plants had begun developing relationships with insects, offering nectar and other rewards in exchange for pollination services. These early partnerships between plants and insects would eventually evolve into some of the most intricate cooperative relationships in the natural world. The seasonal patterns of the mid-Jurassic world created additional layers of complexity. The climate wasn't uniformly warm and stable. There were definite seasons, with some areas experiencing cold winters that could even include snow and ice formation. These seasonal changes created migration patterns, reproductive cycles, and behavioral adaptations that added yet another dimension to the ecosystem's complexity. During the warmer months, life exploded across the landscape. Plants grew rapidly, producing the massive quantities of vegetation needed to support the giant herbivores. Reproduction peaked during these favorable periods, with many species timing their breeding cycles to take advantage of abundant food resources and favorable weather conditions. As we piece together the story of the mid-Jurassic period, what emerges is a picture of a world that was not just different from our own, but almost impossibly rich and complex. Every square mile of land and sea was teeming with life forms that had evolved incredible specializations for survival and success. The creatures of this period weren't just bigger or smaller versions of modern animals. They were entirely different solutions to the challenges of existence, representing evolutionary experiments that pushed the boundaries of what was possible in the natural world. From the impossibly long necks of the sauropods to the precision-engineered killing machines that were the large predators, every species represented a unique approach to the fundamental challenge of staying alive and reproducing successfully. What makes this period even more remarkable is that it was all temporary. The continental movements that had created the perfect conditions for these incredible creatures were continuing to reshape the planet. Climate patterns were shifting, sea levels were changing, and new evolutionary pressures were building that would eventually transform this amazing world into something completely different. But perhaps the most fascinating aspect of the mid-Jurassic world wasn't the giants that dominated the headlines of paleontological discovery. It was the incredible array of smaller, more unusual creatures that revealed just how creative evolution can become when given the right conditions and enough time to experiment. Let's talk about one of the most intriguing evolutionary stories of this period: the rise of the first truly social insects. While we often think of ants and bees as relatively modern innovations, the Mid-Jurassic was already witnessing the early experiments in collective behavior that would eventually lead to some of nature's most sophisticated societies. These early social insects weren't building the massive colonies we associate with modern species, but they were developing the basic cooperative behaviors that would become their trademark. Small groups of insects began working together to construct primitive nests, share food resources, and defend their territories from competitors. It's mind-boggling to think that while massive dinosaurs were battling for dominance above ground, tiny insects were quietly revolutionizing social organization in ways that would eventually influence ecosystems across the entire planet. The aquatic invertebrates of this period tell an equally compelling story of evolutionary innovation. The warm seas were absolutely packed with creatures that were experimenting with completely new approaches to marine life. Ancient relatives of modern octopi were developing the intelligence and problem-solving abilities that would make their descendants some of the most remarkable creatures in our modern oceans. But here's where things get really weird. Some of these early cephalopods were evolving in directions that would seem completely alien to us today. Imagine an octopus-like creature with a shell that could grow to enormous sizes, creating mobile fortresses that cruised through ancient seas. These weren't just slightly different versions of creatures we know. They were entirely unique solutions to the challenges of underwater predation and survival. The ammonites represent perhaps the most successful of these experimental designs. With their coiled shells and sophisticated jet propulsion systems, they had mastered three-dimensional movement through water in ways that put most modern marine creatures to shame. Some species developed shells with incredibly complex internal chambers that could be precisely adjusted to control buoyancy, allowing them to hover at exact depths while hunting or avoiding predators. What species had evolved completely different shell shapes is absolutely remarkable is that different AM for different ecological niches. Some had smooth, streamlined shells designed for speed and efficiency in open water. Others developed elaborate spikes and ridges that served as defensive armor against the massive marine predators of their time. Still others evolved shells with bizarre geometric patterns that we're still trying to understand. The diversity of these shell designs reveals something profound about mid-Jurassic marine ecosystems. Every possible survival strategy was being explored simultaneously. It was like evolution was running thousands of different experiments at the same time, testing every conceivable approach to staying alive in an incredibly dangerous underwater world. But let's shift our focus back to the terrestrial realm, because some of the most bizarre dinosaur discoveries come from creatures that don't fit neatly into our traditional categories of herbivore and carnivore. The Mid Jurassic produced dinosaurs that were experimenting with dietary strategies that would make modern nutritionists scratch their heads in confusion. Consider the theropods that were beginning to incorporate plant material into their diets. These weren't the classic meat-eating predators we often imagine. Instead, they were developing increasingly complex digestive systems that could process both animal protein and plant matter. Some species were evolving specialized teeth that could both slice through flesh and grind tough vegetation, creating omnivorous capabilities that gave them incredible flexibility in finding food. This dietary flexibility was crucial during periods when prey animals might be scarce, or when seasonal changes affected the availability of different food sources. A dinosaur that could switch between hunting small animals and foraging for fruits, seeds, and tender shoots had a massive survival advantage over more specialized feeders. But the really unusual dietary experiments were happening among some of the smaller dinosaur species. Paleontologists have discovered evidence of dinosaurs that were developing incredibly specialized feeding strategies. Some were evolving elongated snouts and delicate teeth that seemed perfectly designed for extracting insects from tree bark and crevices. Others were developing robust jaw muscles and reinforced skulls that suggest they were cracking open hard nuts and seeds with incredible force. One of the most puzzling groups from this period were the dinosaurs that seem to have been experimenting with filter feeding. These creatures had developed strange comb-like structures in their mouths that appear designed for straining small organisms from water. Imagine a dinosaur that fed like a modern flamingo, wading through shallow waters while filtering out tiny crustaceans and other aquatic life forms. The existence of such creatures reveals just how diverse aquatic and semi-aquatic environments were during the Mid-Jurassic. These weren't just simple lakes and rivers. They were complex wetland ecosystems that supported an incredible variety of life forms, from microscopic organisms to massive predators. The pterosaurs of this period were equally experimental in their approaches to flight and feeding. While we often think of these creatures as simple flying reptiles, the mid-Jurassic species were developing incredibly sophisticated adaptations that allowed them to exploit aerial niches in ways that would make modern pilots envious. Some pterosaur species were evolving incredibly precise flight control systems. Their wing membranes weren't just simple flaps of skin. They were complex structures with intricate muscle arrangements that allowed for incredibly fine adjustments in flight dynamics. These creatures could probably hover in place, make sharp turns at high speeds, and adjust their wing shape to optimize for different flight conditions. But perhaps most remarkably, some pterosaurs were developing feeding strategies that required incredible aerial precision. Evidence suggests that certain species were evolving the ability to snatch prey from the surface of water bodies while in full flight, a technique that requires split-second timing and extraordinary coordination between vision, flight control, and feeding mechanisms. Other pterosaur species were taking completely different approaches to aerial hunting. Some were developing increasingly robust skulls and powerful jaw muscles that suggest they were capable of crushing the shells of large marine invertebrates. Imagine a pterosaur that could dive into the ocean, grab a massive ammonite, and then use its powerful jaws to crack open the shell while still in flight. The diversity of pterosaur hunting strategies reveals something important about mid-Jurassic ecosystems. There was an incredible abundance of flying prey. The skies weren't empty spaces that pterosaurs had to themselves. They were filled with countless insects, early flying reptiles, and other airborne creatures that created complex three-dimensional food webs. Some of the most unusual pterosaurs were developing social behaviors that seem surprisingly sophisticated. Evidence suggests that certain species were beginning to hunt in coordinated groups using communication calls and collaborative strategies to take down prey that would be impossible for individual hunters to manage. This brings us to one of the most fascinating aspects of mid-Jurassic life: the development of increasingly complex communication systems across many different animal groups. The soundscape of this ancient world would have been absolutely incredible, filled with calls, songs, and signals that we can barely imagine. The large sauropods were probably producing sound that could travel for miles across the landscape. With their enormous size and specialized vocal equipment, they could generate low-frequency calls that would penetrate through forests and across valleys, allowing herds to maintain contact even when separated by vast distances. These long-distance communication systems would have been crucial for coordinating migrations, warning of dangers, and facilitating the social behaviors that allowed these massive animals to survive in groups. The ability to communicate across great distances also meant that individual sauropods could benefit from the collective knowledge of their entire population, learning about food sources, water locations, and predator movements from animals they might never actually see. The predatory dinosaurs were developing equally sophisticated communication strategies, but for very different purposes. Evidence suggests that some species were beginning to coordinate their hunts, using complex vocal signals, allowing them to surround prey, drive animals into ambush locations, and share information about the movements of potential targets. But the really intriguing communication developments were happening among the smaller dinosaurs and early mammals. These creatures were evolving incredibly diverse vocal repertoires that served multiple functions simultaneously. The same call might convey information about food sources, warn of approaching predators, signal reproductive readiness, and maintain social bonds within family groups. The complexity of these communication systems reveals something profound about mid-Jurassic animal intelligence. These weren't simple creatures operating on basic instincts. They were developing cognitive abilities that allowed them to process complex information, make sophisticated decisions, and adapt their behavior based on changing circumstances. The marine environments were equally rich in communication innovations. The large marine reptiles were probably using low-frequency calls that could travel through water for enormous distances, creating acoustic networks that connected animals across entire ocean basins. Some of the most sophisticated communication was probably happening among the schooling fish and marine invertebrates. These creatures were developing collective behaviors that required incredibly precise coordination between thousands of individuals. The ability to move as a unified group while responding instantly to threats and opportunities represents a level of collective intelligence that still amazes modern researchers. But let's return to one of the most puzzling aspects of mid-Jurassic dinosaur evolution: the development of increasingly elaborate display structures. Many species were evolving features that seemed to serve no obvious survival function, but were clearly important for social interactions and reproductive success. Some dinosaurs were developing colorful crests, elaborate frills, and bizarre ornamental structures that must have played crucial roles in species recognition and mate selection. These weren't just random decorative features. They were sophisticated signaling devices that conveyed information about an individual's health, genetic quality, and social status. The energy investment required to grow and maintain these ornamental features was enormous. Only the healthiest, most successful individuals could afford to develop truly impressive displays, which meant that these structures served as reliable indicators of overall fitness and desirability as mates. But the most unusual display structures were probably dynamic rather than static. Some dinosaurs were evolving the ability to change their coloration, inflate air sacs, or manipulate flexible body parts to create incredibly dramatic visual displays. Imagine a dinosaur that could transform its appearance as dramatically as a modern chameleon, but on a scale that would be visible from hundreds of meters away. These dynamic display capabilities would have created incredibly rich and complex social interactions. Individual dinosaurs could communicate their intentions, emotional states, and social positions through subtle changes in their appearance, creating a visual language that was far more sophisticated than anything we see in most modern reptiles. The development of these communication and display systems reveals something crucial about mid-Jurassic ecosystems. They were becoming increasingly social and interactive. Animals weren't just competing for resources and avoiding predators. They were developing complex relationships with members of their own species and even with other species that shared their environments. Some of the most intriguing evidence suggests that certain dinosaur species were beginning to develop mutualistic relationships with other animals. Small dinosaurs might have served as cleaners for larger species, removing parasites and dead skin in exchange for protection and access to food scraps. Flying pterosaurs might have followed migrating herds, feeding on insects disturbed by the movement of large animals, while also serving as early warning systems for approaching predators. These cooperative relationships represent some of the earliest examples of the complex ecological partnerships that would eventually become common in later ecosystems. The ability to form beneficial relationships with other species provided significant survival advantages and opened up entirely new ecological niches that couldn't be exploited by solitary animals. The plant life of the mid-Jurassic was equally innovative in developing relationships with animal partners. Some plants were beginning to evolve fruits and seeds that were specifically designed to be attractive to certain animal species, ensuring widespread dispersal of their genetic material in exchange for providing nutritious food rewards. Other plants were developing defensive partnerships with insects, providing shelter and food for aggressive species that would attack any herbivores attempting to feed on their leaves. These early examples of plant-animal cooperation would eventually evolve into some of the most sophisticated ecological relationships on our planet. But perhaps the most remarkable aspect of mid-Jurassic innovation was the development of increasingly sophisticated parental care behaviors. Many dinosaur species were evolving complex nesting strategies, elaborate brooding behaviors, and extended periods of offspring care that far exceeded anything seen in modern reptiles. Some species were building incredibly sophisticated nests with multiple chambers, drainage systems, and temperature regulation features that ensured optimal conditions for egg development. Others were developing the ability to precisely control the temperature and humidity of their nesting sites, allowing them to successfully reproduce in a much wider range of environmental conditions. The most advanced species were beginning to provide extended care for their young, teaching them essential survival skills, protecting them from predators, and even sharing food resources long after hatching. This investment in offspring care represented a fundamental shift in reproductive strategy that would eventually become one of the key factors in dinosaur evolutionary success. The diversity of parental care strategies reveals just how many different approaches to reproduction were being tested during this period. Some species were focusing on producing large numbers of offspring with minimal individual care, betting on the survival of a few individuals through sheer numbers. Others were investing heavily in smaller numbers of young, providing intensive care that dramatically increased the survival chances of each individual. These different reproductive strategies created complex population dynamics that influenced every aspect of mid-Jurassic ecosystems. Species with high reproductive rates could rapidly colonize new habitats and recover quickly from population crashes, while species with intensive parental care could maintain stable populations in challenging environments and develop increasingly sophisticated behaviors across generations. The interplay between these different reproductive strategies created incredibly dynamic ecosystems, where population levels, predator-prey relationships, and resource availability were constantly shifting in response to environmental changes and evolutionary innovations. As we delve deeper into the mysteries of the mid-Jurassic world, what becomes clear is that this wasn't just a period of bigger animals and different climates. It was a time of unprecedented biological innovation, when evolution was experimenting with solutions to survival challenges that pushed the boundaries of what seemed possible in the natural world. Every aspect of life, from the microscopic to the gigantic, was undergoing rapid transformation and specialization. The creatures that emerged from this period weren't just adapted to their environments. They were actively reshaping those environments through their behaviors, interactions, and ecological relationships. The complexity and sophistication of mid-Jurassic life forms challenge our understanding of evolutionary timescales and the speed at which complex adaptations can develop in what seems like a relatively short period of geological time, life on Earth had developed solutions to survival challenges that rival anything we see in modern ecosystems. But this incredible world of evolutionary innovation was also incredibly fragile. The same geological and climatic forces that had created perfect conditions for these remarkable creatures were continuing to change, setting the stage for the next chapter in Earth's biological history. The continental movements, climate shifts, and environmental changes that had fostered such incredible diversity were also creating new pressures that would test the adaptability of every species that had evolved during this golden age of biological experimentation. The stage was being set for one of the most dramatic transitions in Earth's history, as the stable, lush world of the Mid Jurassic began its transformation into something entirely different. The creatures that had perfected their survival strategies for this particular set of environmental conditions would soon face challenges that would test the limits of their remarkable adaptations. But understanding the full scope of mid-Jurassic innovation requires us to examine something that most people never consider: the incredible underground world that existed beneath all this surface drama. While massive sauropods thundered across the landscape above, an entirely different realm of biological experimentation was taking place in the soil, caves, and underground waterways of this ancient world. The subterranean ecosystems of the mid-Jurassic were absolutely teeming with life forms that had evolved specifically for existence in complete darkness. These weren't just smaller versions of surface animals that happened to live underground. They were creatures that had undergone radical transformations to thrive in environments where traditional senses like vision became completely useless. Some of the most remarkable adaptations were happening among the early mammalian species that had claimed the underground realm as their primary habitat. These creatures were developing sensory capabilities that would make modern echolocation systems look primitive by comparison. Their whiskers had evolved into incredibly sophisticated tactile networks that could detect the slightest vibrations in soil and rock, allowing them to navigate complex tunnel systems and locate prey with pinpoint accuracy. But the really mind-blowing innovations were happening at the cellular level. These underground mammals were evolving metabolic systems that could function efficiently on incredibly limited oxygen supplies, allowing them to survive in burrow systems that would suffocate surface-dwelling animals within minutes. Their blood chemistry had adapted to carry oxygen with such efficiency that they could remain active in environments where the air was almost completely depleted of breathable gases. The tunnel systems themselves were marvels of biological engineering. Some mammalian species were creating underground networks that stretched for miles, with specialized chambers for food storage, nurseries for raising young, and even areas that seemed designed for social gatherings. These weren't random holes in the ground. They were sophisticated architectural projects that required planning, cooperation, and maintenance across multiple generations. What's absolutely fascinating is that these underground ecosystems were supporting their own unique food webs that operated completely independently of surface conditions. Specialized fungi had evolved to break down organic matter that filtered down from above, creating the foundation for entire communities of underground organisms. Some of these fungi were developing bioluminescent capabilities, creating underground environments that glowed with their own ethereal light. The arthropods of the underground realm had evolved into forms that would seem completely alien to anyone familiar with their surface relatives. Some had developed incredibly elongated limbs that allowed them to navigate through narrow crevices and detect prey or predators from enormous distances. Others had evolved specialized chemical sensors that could detect the presence of food sources or potential mates through incredibly subtle changes in their chemistry. But perhaps the most remarkable underground creatures were the ones that had learned to exploit the unique geological features of the Mid Jurassic world. The constant tectonic activity was creating underground hot springs, mineral deposits, and geothermal vents that provided entirely new energy sources for biological systems. Some organisms were evolving the ability to derive energy directly from chemical processes involving sulfur compounds and other minerals that were abundant in these geologically active areas. This chemosynthetic capability allowed them to survive completely independently of sunlight and photosynthesis, creating biological communities that could theoretically survive even if the surface world was completely destroyed. The implications of these underground innovations extend far beyond simple survival strategies. These creatures were developing biological technologies that wouldn't be rediscovered by surface life forms for millions of years. Their ability to navigate in complete darkness, communicate through chemical signals, and derive energy from inorganic sources represent some of the most advanced biological engineering ever developed. Now, let's shift our attention to another realm that was undergoing equally dramatic innovations: the microscopic world that formed the invisible foundation of all mid-Jurassic life. While we often focus on the giants that dominated the landscape, the real evolutionary revolution was happening at scales so small that we're only now beginning to understand their importance. The bacterial and microbial communities of the mid-Jurassic were developing capabilities that would fundamentally change the chemistry of Earth's atmosphere, oceans, and soil systems. Some bacterial species were perfecting new methods of nitrogen fixation that made previously sterile soils incredibly fertile, supporting the explosive plant growth that fed the massive herbivorous dinosaurs. Other microbial communities were developing sophisticated cooperative relationships that allowed them to break down organic compounds that had previously been completely indestructible. These biological recycling systems were so efficient that they could process the enormous quantities of organic waste produced by the giant dinosaurs, preventing the accumulation of toxic materials that could have poisoned entire ecosystems. But the most revolutionary microbial innovations were happening in the digestive systems of the herbivorous dinosaurs themselves. The massive sauropods weren't just eating plants and somehow magically extracting nutrition from them. They were hosting incredibly complex microbial communities in their digestive systems, that were capable of breaking down cellulose and other plant materials with unprecedented efficiency. These internal microbial ecosystems were so sophisticated that they were essentially functioning as external organs. Different species of bacteria and other microorganisms were specializing in processing different types of plant materials, working together in carefully orchestrated sequences that could extract maximum nutritional value from even the toughest, most fibrous vegetation. The development of these symbiotic relationships between dinosaurs and their internal microbial communities represents one of the most important evolutionary innovations of the Mid Jurassic Period. It allowed herbivorous dinosaurs to grow to sizes that would have been impossible without incredibly efficient digestive systems, and it created biological partnerships that were so successful they would persist for millions of years. But the microbial innovations weren't limited to digestive assistance. Some bacterial communities were developing the ability to produce antibiotics and other defensive compounds that helped protect their dinosaur hosts from diseases and infections. Others were synthesizing vitamins and other essential nutrients that supplemented the dinosaurs' diets and supported their incredible growth rates. The complexity of these microscopic relationships reveals something profound about the interconnectedness of mid-Jurassic life. Every large animal was actually a walking ecosystem, supporting thousands of different microbial species that contributed to its survival and success. The health and behavior of the giant dinosaurs was intimately connected to the well-being of countless microscopic partners that most people never even think about. This microscopic dimension of mid-Jurassic life also helps explain some of the more puzzling aspects of dinosaur behavior and physiology. The incredible migrations undertaken by sauropod herds weren't just searches for food and water. They were also journeys that allowed different dinosaur populations to exchange microbial communities, maintaining the genetic diversity of their internal ecosystems and preventing the development of harmful bacterial imbalances. The social behaviors of many dinosaur species were probably influenced by the need to maintain healthy microbial communities. Young dinosaurs would have needed to acquire their essential digestive bacteria from their parents and other herd members, creating social bonds that served biological functions far beyond simple protection and education. Some of the most unusual dinosaur behaviors were probably related to microbial management. Certain species seem to have engaged in deliberate consumption of specific types of soil and rock, probably to acquire minerals and bacterial cultures that were essential for maintaining their internal ecosystems. The evidence for these microbial relationships comes from some fascinating paleontological discoveries that reveal the incredible sophistication of mid-Jurassic biological systems. Fossilized dinosaur coprolites contain preserved bacterial communities that show clear evidence of specialized digestive partnerships, while fossilized gastroliths reveal that dinosaurs were actively managing their internal environments in ways that rival the most advanced modern agricultural techniques. But let's expand our perspective even further to consider the atmospheric and climatic innovations that were happening during this period. The mid-Jurassic world wasn't just supporting more life than any previous period in Earth's history. It was also actively modifying the planet's atmospheric chemistry in ways that created feedback loops that supported even more biological diversity. The massive forests of this period were producing oxygen at rates that significantly exceeded modern levels, creating atmospheric conditions that could support much larger animals and more active metabolisms. The higher oxygen concentrations meant that even the largest dinosaurs could maintain active lifestyles without the respiratory limitations that would affect similar-sized animals in our current atmosphere. But the really fascinating atmospheric innovations were happening through the interactions between plant and animal communities. The massive herds of herbivorous dinosaurs were creating complex patterns of vegetation management that maintained optimal forest compositions for both plant growth and animal nutrition. Their feeding behaviors were essentially functioning as large-scale ecological engineering projects that shaped entire landscapes. Different dinosaur species were specializing in consuming different types of vegetation at different stages of plant growth, creating carefully managed succession patterns that maximized both plant productivity and animal nutrition. Some species were essentially functioning as biological lawnmowers, keeping grasslands and open areas from being overtaken by forest growth. Others were serving as selective foresters, removing certain tree species while promoting the growth of others. These vegetation management activities were creating incredibly complex mosaic landscapes where different plant communities existed in carefully maintained balance. The result was an environment that could support far more animal species than would be possible in more homogeneous ecosystems. The herbivorous dinosaurs were also contributing to atmospheric regulation through their massive production of methane and other gases. While this might sound like a negative environmental impact, the atmospheric chemistry of the mid-Jurassic period was apparently capable of processing these gases in ways that actually enhanced rather than degraded environmental conditions. The warm, humid climate was supporting atmospheric chemical processes that converted dinosaur-produced methane into compounds that enhanced plant growth and atmospheric stability. The entire system was functioning as a massive biological machine that was actively maintaining optimal conditions for continued life and growth. But perhaps the most remarkable aspect of mid-Jurassic atmospheric management was the role played by the marine ecosystems. The warm oceans were supporting massive populations of microscopic organisms that were actively regulating atmospheric chemistry through their metabolic processes. These marine microorganisms were producing compounds that helped maintain optimal atmospheric moisture levels, regulated temperature through cloud formation, and even influenced seasonal weather patterns through their effects on ocean currents and evaporation rates. The oceans weren't just passive bodies of water that happened to support life. They were active participants in planetary climate regulation that were helping to maintain the stable conditions that allowed terrestrial life to flourish. The integration between terrestrial and marine climate regulation systems was so sophisticated that it created a planet-wide environmental management system that could respond to and compensate for local changes in conditions. If drought affected one region, atmospheric and oceanic processes would redirect moisture from other areas to maintain overall ecosystem stability. This global environmental management system helps explain why the Mid Jurassic Period was able to support such incredible biological diversity for such an extended period of time. The planet had essentially evolved into a self-regulating system where biological processes actively maintained optimal conditions for continued life and evolution. But let's return our focus to some of the most unusual and specialized dinosaur adaptations that were developing during this period of incredible environmental stability. With basic survival needs reliably met by the planet's efficient life support systems, evolution was free to experiment with increasingly specialized and sophisticated adaptations. Some dinosaur species were developing sensory capabilities that would seem almost supernatural by modern standards. Certain predatory dinosaurs were evolving electromagnetic sensitivity that allowed them to detect the bioelectric fields generated by potential prey animals. This electrical sense was so precise that these predators could track animals through dense vegetation or even locate prey that was hiding underground. Other species were developing infrared detection capabilities that allowed them to hunt effectively in complete darkness or track prey through thermal signatures that were invisible to conventional vision. These thermal hunters could detect the body heat of potential prey from enormous distances, giving them hunting capabilities that exceeded anything found in modern predators. But perhaps the most remarkable sensory innovations were happening among the herbivorous species. Some sauropods were developing incredibly sophisticated chemical analysis capabilities that allowed them to assess the nutritional content and safety of potential food sources through subtle chemical signatures. These chemical senses were so precise that the dinosaurs could determine not only whether a plant was nutritious, but also whether it contained toxins, was infected with harmful microorganisms, or was at the optimal stage of growth for maximum nutritional value. The development of these advanced sensory capabilities was creating increasingly sophisticated behavioral patterns that required considerable intelligence to coordinate and manage. Dinosaurs with multiple advanced senses had to develop neural processing systems that could integrate information from electromagnetic, thermal, chemical, and traditional sensory inputs to create comprehensive understanding of their environments. Some species were developing problem-solving abilities that rivaled those of modern intelligent animals. Evidence suggests that certain dinosaurs were capable of using tools, modifying their environments to improve hunting or feeding efficiency, and even engaging in deliberate deception to confuse predators or prey. The social implications of these cognitive advances were equally remarkable. Intelligent dinosaurs were developing increasingly complex social structures that included sophisticated communication systems, cooperative hunting strategies, and even what appears to be cultural transmission of learned behaviors across generations. Some dinosaur communities were developing traditions and customs that were passed down from parents to offspring, creating cultural evolution that operated alongside biological evolution. These cultural innovations allowed dinosaur communities to adapt to changing conditions much more rapidly than would be possible through genetic changes alone. The evidence for dinosaur intelligence and culture comes from some of the most exciting recent paleontological discoveries. Fossil sites have revealed tool use, deliberate construction projects, and evidence of complex social behaviors that suggest cognitive capabilities far beyond what was previously thought possible for reptilian animals. But the most intriguing evidence for dinosaur intelligence comes from their apparent ability to engage in long-term planning and environmental modification. Some species were clearly engaging in landscape engineering projects that required planning and coordination across multiple generations to complete. These long-term projects included the construction of elaborate nesting colonies, the modification of watercourses to create optimal feeding areas, and even what appears to be deliberate forest management to maintain preferred habitat conditions. The scale and sophistication of these projects suggests planning abilities and cooperative capabilities that challenge our understanding of reptilian intelligence. The existence of such sophisticated behavioral capabilities among mid-Jurassic dinosaurs helps explain how they were able to maintain such successful and stable ecosystems for such extended periods of time. These weren't just animals responding to immediate survival pressures. They were intelligent creatures actively managing their environments to ensure long-term success and sustainability. As we piece together this incredibly complex picture of mid-Jurassic life, what emerges is a vision of biological sophistication that exceeds anything we see in modern ecosystems. Every aspect of life, from the microscopic to the massive, was operating at levels of efficiency and integration that represent the peak of evolutionary achievement. The creatures of this period had solved fundamental challenges of existence in ways that allowed them to create stable, sustainable communities that could persist for millions of years while continuously innovating and adapting to changing conditions. They had developed biological technologies, social systems, and environmental management strategies that maintained planetary conditions optimal for continued evolution and diversification. But this remarkable world was not destined to last forever. The same geological and climatic forces that had created the perfect conditions for mid-Jurassic life were continuing to operate, gradually transforming the planet in ways that would challenge even the most sophisticated adaptations that evolution had developed. The continental drift that had created the warm, stable climate was continuing to reshape the planet's geography. Ocean currents were beginning to change as continents moved to new positions. Mountain ranges were continuing to rise, altering weather patterns and creating new climatic zones that would require entirely different survival strategies. The atmospheric chemistry that had supported such incredible biological productivity was beginning to shift as the planet's geological systems evolved. The delicate balance between atmospheric gases, ocean chemistry, and biological processes that had maintained optimal conditions was becoming increasingly unstable. Even the most sophisticated environmental management systems that life had developed were beginning to struggle with the magnitude of changes that were affecting the entire planet. The biological mechanisms that had successfully regulated climate and atmospheric conditions for millions of years were reaching the limits of their adaptive capabilities. The stage was being set for one of the most dramatic transformations in Earth's biological history. The incredible diversity and sophistication of mid-Jurassic life would soon face challenges that would test every adaptation, every survival strategy, and every biological innovation that evolution had developed during this remarkable period of experimentation and success. The question that would determine the future of life on Earth was whether the incredible biological technologies and adaptive capabilities that had been perfected during the mid-Jurassic would be sufficient to meet the unprecedented challenges that were approaching. The answers to this question would reshape the entire trajectory of evolution and determine which of these remarkable creatures would survive to influence the future development of life on our planet. The transition from the stable, productive world of the mid-Jurassic to whatever came next would test the ultimate limits of biological adaptation and reveal whether the sophisticated life forms that had flourished during this golden age of evolution possessed the flexibility and resilience necessary to survive in a rapidly changing world. But that transformation and the incredible story of how these remarkable creatures responded to the ultimate test of their evolutionary innovations represents the next chapter in one of the most dramatic stories in the history of life on Earth. The evidence for these dramatic environmental shifts is written in stone, quite literally, in fossil deposits that tell the story of a world in transition. What scientists have discovered is that the mid-Jurassic wasn't just ending gradually, it was building toward a crescendo of change that would fundamentally alter every aspect of life on Earth. The first signs of this transformation were appearing in the plant communities that formed the foundation of all terrestrial ecosystems. The massive carnivorous forests that had supported the giant sauropods were beginning to show stress patterns that indicated significant changes in growing conditions. Tree ring analysis from fossilized specimens reveals periods of stunted growth, unusual seasonal patterns, and chemical compositions that suggest the plants were struggling to adapt to shifting atmospheric conditions. But the plants weren't passive victims of environmental change. They were actively evolving new strategies to cope with the increasingly unstable conditions. Some species were developing more efficient water storage systems, allowing them to survive longer periods of drought. Others were experimenting with new reproductive strategies that could ensure genetic survival, even if individual plants or entire forests were destroyed by environmental catastrophes. The most innovative plant species were beginning to develop what we might recognize as the earliest flowering mechanisms. While true flowering plants wouldn't dominate for millions of years, the mid-Jurassic was witnessing the first experiments in more efficient pollination and seed dispersal strategies that would eventually revolutionize terrestrial ecosystems. These botanical innovations were creating ripple effects throughout the entire food web. Herbivorous dinosaurs that had specialized in feeding on specific types of vegetation suddenly found their preferred food sources becoming scarce, or changing in nutritional content. This forced rapid behavioral adaptations that tested the limits of their flexibility and intelligence. Some sauropod species were expanding their dietary ranges, learning to process plant materials that had previously been ignored or avoided. Others were modifying their migration patterns, traveling greater distances to find suitable feeding areas as local vegetation communities changed. The most adaptable species were developing enhanced communication systems that allowed herds to share information about food sources across even greater distances than before. But the herbivores weren't the only ones feeling pressure from these environmental changes. The predatory dinosaurs were facing their own set of challenges as prey populations shifted and traditional hunting grounds became less reliable. The massive predators that had perfected their hunting strategies for the stable conditions of the Mid Jurassic were finding that their specialized adaptations were becoming liabilities in a rapidly changing world. Some predatory species were responding by becoming more opportunistic in their feeding habits. Instead of focusing on specific prey species, they were developing the ability to hunt a wider variety of animals, from small mammals to marine reptiles that ventured into coastal areas. This dietary flexibility required significant changes in hunting strategies and social behaviors. Other predators were evolving enhanced mobility, developing the ability to cover greater distances in search of prey populations that were becoming increasingly scattered and unpredictable. These long-distance hunters were developing navigation abilities that allowed them to track prey migrations across continents, following herds through seasonal movements that were becoming increasingly complex as environmental conditions destabilized. The marine ecosystems were experiencing equally dramatic transformations, but in some ways they were proving more resilient than their terrestrial counterparts. The vast oceans provided thermal stability that buffered against some of the more extreme environmental changes affecting land-based communities. However, this apparent stability was masking fundamental changes in ocean chemistry and current patterns that would eventually have profound effects on marine life. The warm seas that had supported such incredible diversity of marine reptiles were beginning to experience temperature fluctuations that affected the distribution of prey species. The massive plesiosaurs that had dominated marine ecosystems were finding that their preferred hunting grounds were shifting as ocean currents changed and upwelling patterns altered the distribution of nutrients and microscopic organisms that form the base of the marine food web. Some marine reptile species were responding to these changes by developing enhanced diving capabilities that allowed them to access deeper water environments where conditions remained more stable. These deep water adaptations included improved pressure tolerance, enhanced oxygen storage capacity, and modified sensory systems that could function effectively in the permanent darkness of the deep ocean. Other marine species were evolving improved thermoregulation systems that allowed them to maintain active lifestyles even as water temperatures became more variable. These physiological innovations included more efficient circulatory systems, improved insulation, and metabolic modifications that could maintain optimal body temperature across a wider range of environmental conditions. But perhaps the most remarkable marine adaptations were happening among the smaller, more numerous species that formed the foundation of ocean food webs. Microscopic organisms were developing incredibly rapid evolutionary responses to changing ocean chemistry, evolving new metabolic pathways and defensive mechanisms in response to environmental pressures that were operating on time scales far shorter than traditional evolutionary processes. These rapid microbial adaptations were creating cascading effects throughout marine ecosystems as changes in the base of the food web propagated upward to affect every level of marine life. The result was a period of incredible evolutionary experimentation in marine environments, with new species appearing and disappearing at rates that exceeded anything seen in terrestrial ecosystems. The atmospheric changes that were driving many of these biological transformations were themselves the result of complex interactions between geological processes, biological systems, and astronomical factors that were operating on multiple time scales simultaneously. The breakup of Pangaea was continuing to accelerate, creating new ocean basins and mountain ranges that were fundamentally altering global weather patterns. Volcanic activity was increasing as tectonic forces intensified, pumping enormous quantities of gases and particulates into the atmosphere that were affecting both local and global climate conditions. Some volcanic eruptions were so massive that they created temporary climate changes that lasted for years or even decades, forcing rapid adaptations among organisms that had evolved for stable conditions. The changing positions of the continents were also affecting ocean circulation patterns in ways that redistributed heat and nutrients around the planet. Currents that had remained stable for millions of years were shifting or disappearing entirely, creating new climate zones and eliminating others that had supported specific biological communities. These geological and climatic changes were happening simultaneously with astronomical events that were affecting the amount and distribution of solar radiation reaching Earth's surface. Variations in Earth's orbit and axial tilt were creating long-term cycles in seasonal patterns that were interacting with the more immediate effects of continental drift and volcanic activity. The combination of all these factors was creating environmental pressures that exceeded the adaptive capabilities of even the most sophisticated biological systems. The planetary environmental management systems that had maintained stable conditions during the height of the Mid Jurassic were being overwhelmed by the magnitude and complexity of the changes they were trying to regulate. Some of the most dramatic evidence for these environmental pressures comes from changes in dinosaur behavior patterns that are preserved in the fossil record. Nesting sites that had been used successfully for millions of years were being abandoned as local environmental conditions became unsuitable for reproduction. Migration routes that had connected distant populations were being disrupted as geographic barriers appeared or familiar landmarks disappeared. The social structures that had allowed dinosaur communities to thrive were beginning to break down under the stress of constant environmental uncertainty. Herds that had maintained stable territories for generations were being forced to compete with displaced populations from other regions, creating conflicts that disrupted traditional social hierarchies and cooperative relationships. Some dinosaur species were responding to these social pressures by developing more aggressive territorial behaviors, defending smaller areas more intensively, rather than attempting to maintain the large ranges that had been possible during more stable times. Others were moving toward more nomadic lifestyles, abandoning fixed territories entirely in favor of continuous movement that allowed them to exploit temporary resource opportunities as they appeared. The most successful species were those that could rapidly modify their social structures in response to changing conditions. Some were developing more flexible hierarchies that could reorganize quickly as group composition changed due to environmental pressures. Others were experimenting with entirely new forms of social organization that had never been seen during the stable period of mid-Jurassic dominance. These behavioral adaptations were requiring significant cognitive evolution as dinosaurs developed enhanced problem-solving abilities and social intelligence to navigate increasingly complex and unpredictable environmental and social situations. Some species were showing evidence of cultural evolution that was accelerating far beyond the pace of genetic change, as learned behaviors and innovative solutions spread rapidly through populations under pressure. The evidence for this accelerated cultural evolution comes from archaeological evidence that shows rapid changes in tool use, nesting construction techniques, and hunting strategies that occurred far too quickly to be explained by genetic evolution alone. Dinosaur communities were essentially developing technological solutions to environmental challenges, creating and sharing innovations that enhanced survival capabilities. But even the most intelligent and adaptable dinosaur species were finding that their individual capabilities were insufficient to address the magnitude of environmental changes they were facing. Some were beginning to develop unprecedented levels of interspecies cooperation, forming alliances with other dinosaur species and even with non-dinosaurian animals to share resources and coordinate responses to environmental threats. These interspecies partnerships were creating entirely new ecological relationships that had never existed during the stable period of mid-Jurassic evolution. Predator species were sometimes cooperating with herbivores to track resource availability, while competing species were sharing territory and resources during particularly challenging environmental periods. The most remarkable of these cooperative relationships were forming between terrestrial and marine species. Some coastal dinosaur populations were developing partnerships with marine reptiles, sharing information about environmental conditions and resource availability across the land-sea boundary. These relationships were facilitated by the enhanced communication abilities that many species had developed in response to environmental pressures. The flying pterosaurs were playing increasingly important roles in these cooperative networks, serving as long-distance messengers that could rapidly transmit information about environmental conditions and resource availability across vast geographic areas. Some pterosaur species were specializing in this communication role, developing enhanced memory and navigation abilities that allowed them to maintain complex information networks spanning entire continents. These biological information networks were becoming so sophisticated that they were functioning almost like primitive technological systems, allowing widely separated animal communities to coordinate their responses to environmental changes and share successful adaptation strategies. The speed at which information could travel through these networks was enabling evolutionary innovations to spread across species boundaries at unprecedented rates. But despite all these remarkable adaptations and innovations, the fundamental challenge remained. The environmental changes that were ending the Mid Jurassic Period were operating at scales and speeds that exceeded the adaptive capabilities of even the most sophisticated biological systems. The same geological forces that had created the perfect conditions for mid-Jurassic life were now creating conditions that would require entirely different survival strategies. The continental movements that were reshaping the planet's geography were creating new mountain ranges that were blocking traditional migration routes and creating rain shadows that were turning previously lush regions into deserts. Ocean basins that had supported stable marine ecosystems for millions of years were draining or being filled with sediment, forcing massive redistributions of marine life. The atmospheric changes that were accompanying these geological transformations were altering not just climate patterns, but the basic chemistry of the air and water that all life depended upon. Oxygen concentrations were beginning to fluctuate in ways that affected the metabolic capabilities of large animals, while carbon dioxide levels were shifting in patterns that influenced both plant growth and atmospheric temperature regulation. Some regions of the planet were becoming completely uninhabitable for the types of organisms that had flourished during the mid-Jurassic, while other areas were developing environmental conditions that had never existed before in Earth's history. These novel environments were creating opportunities for entirely new types of organisms, while eliminating the habitats that had supported traditional mid-Jurassic communities. The speed of these environmental changes was particularly challenging for the largest dinosaur species, whose life cycles and reproductive patterns were adapted for stable, long-term conditions. Sauropods that required decades to reach reproductive maturity were finding that environmental conditions could change completely within a single generation, making their traditional life strategies obsolete. The massive size that had been such an advantage during the stable mid-Jurassic was becoming a liability, as environmental changes required rapid mobility and dietary flexibility. Large animals that had thrived on abundant, predictable food sources were struggling to find sufficient nutrition in environments where resource availability was becoming increasingly sporadic and unpredictable. Some of the largest dinosaur species were beginning to show evidence of physiological stress that indicated they were reaching the limits of their adaptive capabilities. Fossil evidence suggests that growth rates were declining, reproductive success was decreasing, and lifespan was shortening as these magnificent creatures struggled to cope with rapidly changing conditions. The smaller, more agile dinosaur species were generally faring better in the changing environment, but they were facing their own set of challenges as the ecological niches they had occupied became unstable or disappeared entirely. Many were being forced to compete directly with early mammalian species that were proving remarkably adaptable to changing conditions. The mammals that had remained small and inconspicuous during the height of dinosaur dominance were beginning to show their true evolutionary potential as environmental conditions favored flexibility and rapid reproduction over size and specialization. Their ability to remain active during cooler periods, their efficient reproductive cycles, and their dietary flexibility were becoming significant advantages in an increasingly unpredictable world. But perhaps the most significant challenge facing all mid-Jurassic life forms was the increasing frequency of catastrophic events that were overwhelming even the most sophisticated adaptation strategies. Massive volcanic eruptions, sudden climate shifts, and geological catastrophes were creating environmental crises that required immediate responses rather than gradual evolutionary adaptations. These catastrophic events were testing the ultimate limits of biological resilience, forcing rapid population bottlenecks that eliminated many of the specialized adaptations that had been perfected during millions of years of stable evolution. Only the most fundamentally robust and adaptable organisms were surviving these crisis events, while highly specialized species were disappearing regardless of how perfectly adapted they had been to previous conditions. The fossil record from the end of the Mid-Jurassic Period reveals a pattern of increasing environmental stress that was affecting every aspect of biological life. Species diversity was beginning to decline as specialized organisms disappeared, while the surviving species were becoming increasingly generalized in their adaptations and behaviors. The complex ecological relationships that had characterized the peak of mid-Jurassic evolution were beginning to break down as key species disappeared and environmental conditions became too unstable to support the intricate partnerships that had developed during more stable times. Food webs were simplifying, communication networks were fragmenting, and the sophisticated environmental management systems that had maintained planetary stability were failing. Yet, even as this remarkable biological civilization was facing its ultimate challenges, evolution was continuing to experiment with new solutions and innovations. The crisis conditions that were ending the mid-Jurassic period were also creating intense selective pressures that were driving rapid evolutionary change in unexpected directions. Some organism groups were undergoing accelerated evolution that was producing entirely new types of adaptations within just a few generations. The combination of environmental pressure and genetic flexibility was creating evolutionary innovations that would not have been possible during the stable conditions of the mid-Jurassic peak. The most successful of these rapid evolutionary experiments were occurring among organism groups that had maintained high levels of genetic diversity and behavioral flexibility throughout the Mid-Jurassic period. These groups were able to rapidly exploit new environmental opportunities as they appeared, while also developing novel survival strategies for dealing with unprecedented challenges. The stage was being set for one of the most dramatic evolutionary transitions in Earth's history. The incredible diversity and sophistication of mid-Jurassic life was about to give way to entirely new forms of biological organization that would be adapted for survival in a much more dynamic and unpredictable world. The organisms that would emerge from this great transition would carry forward some of the innovations and adaptations that had been perfected during the golden age of mid-Jurassic evolution, but they would be combined in new ways and applied to survival challenges that had never been faced before in the history of life on Earth. The question that would determine the future of evolution was whether the biological innovations that had made mid-Jurassic life so successful contained within them the seeds of adaptation that could survive the ultimate test of environmental change. The answer to this question would determine not only which species would survive, but what kinds of organisms would inherit the Earth and shape the future course of biological evolution. The remarkable creatures that had dominated the mid-Jurassic world were facing their greatest challenge, and their response to this challenge would determine whether their incredible legacy of biological innovation would continue into the future or become merely a magnificent chapter in the history of life that had reached its conclusion. The transformation that was beginning would test every assumption about biological success and evolutionary strategy, revealing which adaptations were truly fundamental to survival and which were merely specialized responses to temporary environmental conditions. The results of this test would reshape not only the biological world, but our understanding of what makes life successful in the face of ultimate challenges. As we witness this incredible transformation unfolding across the planet, something absolutely remarkable was happening that most people never consider when they think about the end of the mid-Jurassic period. While the massive environmental changes were creating chaos for many species, they were also triggering one of the most extraordinary evolutionary explosions in Earth's history among a group of creatures that had been quietly waiting in the shadows for their moment to shine. The early birds were about to make their grand entrance onto the world stage, and their arrival would change everything we thought we knew about flight, intelligence, and survival strategies. These weren't just reptiles with wings. They were revolutionary new life forms that combined the best innovations from multiple evolutionary lineages into something completely unprecedented. But here's what makes their emergence even more incredible. These early birds weren't just adapting to the changing world, they were actively taking advantage of the chaos to exploit opportunities that had never existed before. While other species were struggling to cope with environmental instability, the birds were using that same instability as a launching pad for evolutionary innovations that would make them some of the most successful creatures in Earth's history. The first true birds were appearing just as the stable ecosystems of the mid-Jurassic were beginning to fragment. This timing wasn't coincidental. The breakdown of established ecological relationships was creating thousands of new niches that required entirely different survival strategies. The birds were perfectly positioned to exploit these opportunities because they possessed something that no other creatures had: the ability to move rapidly between different environments and resource patches. Imagine having wings in a world where traditional migration routes were being disrupted by geological changes. While ground-based animals were trapped by new mountain ranges and changing river systems, the early birds could simply fly over these obstacles to reach resources that were becoming inaccessible to other creatures. This mobility advantage was so significant that it fundamentally changed the rules of survival. But flight was just the beginning of their revolutionary capabilities. These early birds were developing cognitive abilities that exceeded anything seen in reptiles of their size. Their brains were evolving specialized regions for processing complex spatial information, allowing them to navigate three-dimensional environments with precision that would make modern pilots envious. The neural innovations required for flight were creating unexpected side effects that enhanced intelligence in ways that benefited survival far beyond simple navigation. Birds were developing enhanced memory systems that could store detailed information about resource locations across vast geographic areas. They could remember not just where food sources were located, but when they would be available seasonally, and how environmental conditions affected their quality. This cognitive revolution was enabling birds to develop behavioral strategies that were incredibly sophisticated for their time. Some species were beginning to cache food in multiple locations, creating backup resource reserves that could sustain them through periods when preferred foods became unavailable. Others were developing complex social behaviors that allowed them to share information about resource discovery across extended networks of individuals. The communication systems that birds were evolving were unlike anything that had existed in the mid-Jurassic world. While other animals relied primarily on visual displays or simple vocalizations, birds were developing elaborate acoustic communication systems that could convey detailed information about environmental conditions, resource availability, and potential threats. Some bird species were creating what can only be described as primitive languages, with different calls that referred to specific types of food sources, predator species, and environmental conditions. These vocal communication systems were so sophisticated that they allowed bird communities to coordinate their activities across distances that would have been impossible for ground-based animals to manage. The social implications of these communication innovations were staggering. Bird flocks were becoming information processing networks that could collectively solve problems that would have been impossible for individual animals to address. When one bird discovered a new food source or identified a potential threat, that information could be rapidly transmitted to hundreds or even thousands of other individuals within minutes. This collective intelligence was giving bird communities adaptive capabilities that far exceeded what their individual cognitive abilities would suggest. Flocks were essentially functioning as distributed computing systems, with each individual bird contributing sensory information and processing power. to collective decision-making processes. But the most remarkable aspect of early bird evolution wasn't their flight capabilities or their intelligence. It was their incredible metabolic innovations that allowed them to maintain active lifestyles under environmental conditions that were increasingly challenging for other animals. Birds were developing the first truly efficient warm-blooded metabolisms that could function optimally across a wide range of temperatures and activity levels. This metabolic revolution was made possible by a series of interconnected physiological innovations that represented some of the most sophisticated biological engineering ever developed. Their respiratory systems were evolving into incredibly efficient oxygen extraction mechanisms that could support high-energy activities even in environments where oxygen concentrations were becoming variable. The cardiovascular systems of early birds were undergoing equally dramatic improvements, developing four-chambered hearts that could maintain optimal blood circulation under the demanding conditions of powered flight. These circulatory innovations were so efficient that they could support metabolic rates that were several times higher than anything achievable by reptilian systems. But perhaps most importantly, birds were evolving revolutionary insulation systems that allowed them to maintain optimal body temperatures regardless of environmental conditions. Their feathers weren't just flight surfaces. They were sophisticated thermal regulation systems that could be adjusted dynamically to maintain perfect temperature control under changing conditions. The development of feathers represents one of the most remarkable evolutionary innovations in the history of life. These weren't just modified scales. They were entirely new biological structures that combined multiple functions into integrated systems that exceeded the performance of any previous biological materials. Individual feathers were composed of incredibly complex microscopic structures that could trap air for insulation while also providing the aerodynamic properties necessary for flight. The same feather that kept a bird warm during cold periods could be reconfigured to provide cooling during hot weather and then optimized for flight performance when movement was required. The manufacturing process that created these remarkable structures was equally impressive. Bird skin was evolving specialized follicles that could produce feathers with precisely controlled properties, adjusting their structure, density, and performance characteristics in response to environmental conditions and behavioral needs. Some bird species were developing the ability to produce different types of feathers for different purposes, creating specialized plumage systems that were optimized for specific activities. Flight feathers were engineered for maximum aerodynamic efficiency, while insulation feathers were designed for thermal regulation, and display feathers were created for communication and social signaling. This specialization was requiring increasingly sophisticated genetic control systems that could coordinate the production of multiple feather types while also regulating their replacement and maintenance. Birds were essentially developing biological manufacturing systems that could produce high-performance materials on demand. The implications of these innovations extended far beyond individual survival. Birds were becoming living laboratories for biological material science, developing solutions to engineering challenges that wouldn't be understood by human technology for millions of years. Their feathers were achieving performance characteristics that modern material science still struggles to replicate. But let's shift our focus to another group of creatures that were undergoing equally remarkable transformations during this period of environmental change. The marine ecosystems that had seemed relatively stable compared to terrestrial environments were actually experiencing some of the most dramatic evolutionary innovations of the entire transition period. The large marine reptiles that had dominated mid-Jurassic oceans were facing challenges that were forcing them to develop capabilities that pushed the boundaries of what seemed possible for aquatic animals. Some species were evolving enhanced diving abilities that allowed them to access deep ocean environments that had previously been unexploitable. These deep-sea adaptations weren't just simple modifications of existing capabilities. They required fundamental changes in physiology that allowed these animals to function under extreme pressure conditions while maintaining the sensory and motor capabilities necessary for effective hunting in complete darkness. The pressure-tolerant systems that some marine reptiles were developing involved sophisticated modifications to their circulatory and respiratory systems that could maintain optimal function at depths where the water pressure would crush most organisms. Their blood chemistry was evolving to carry oxygen and other essential compounds under conditions that would be toxic to surface-adapted animals. But the most remarkable deep-sea adaptations were happening in their sensory systems. These marine reptiles were developing echolocation capabilities that allowed them to navigate and hunt in environments where traditional vision was completely useless. Their acoustic sensory systems were becoming so sophisticated that they could create detailed three-dimensional maps of their surroundings using sound waves. Some species were developing bioluminescent capabilities that allowed them to create their own light sources for hunting and communication in the eternal darkness of the deep ocean. These biological lighting systems weren't simple glowing patches. They were sophisticated optical devices that could produce controlled patterns of light for specific purposes. The bioluminescent displays that some marine reptiles were developing were functioning as underwater communication systems that could transmit complex information across vast distances. Different light patterns could convey information about species identity, reproductive status, territorial boundaries, and resource availability. These underwater light shows were creating entirely new forms of social organization among deep-sea creatures. Communities were forming around shared bioluminescent communication protocols, with different species developing compatible signaling systems that allowed for interspecies cooperation in the challenging deep ocean environment. But the innovation wasn't limited to the giants of the marine world. The smaller marine organisms were undergoing equally dramatic evolutionary changes that were reshaping the fundamental structure of ocean ecosystems. Microscopic marine life was developing incredibly rapid evolutionary responses to changing ocean chemistry that were creating cascading effects throughout the entire marine food web. Some microscopic organisms were evolving the ability to switch between completely different metabolic pathways depending on environmental conditions. During periods when traditional food sources became scarce, they could shift to chemosynthetic processes that derived energy from chemical compounds rather than photosynthesis or predation. These metabolic innovations were allowing marine ecosystems to maintain productivity even when traditional nutrient cycles were disrupted by environmental changes. The microscopic organisms were essentially developing backup life support systems that could keep marine food webs functioning during periods when surface conditions became unstable. The rapid evolutionary responses of marine microorganisms were happening at speeds that challenged traditional understanding of evolutionary timescales. Some species were showing significant genetic and physiological changes within just a few generations, adapting to environmental pressures in real time rather than over the millions of years typically required for major evolutionary innovations. This accelerated evolution was made possible by the incredibly short generation times and high reproductive rates of microscopic organisms, combined with environmental pressures that were intense enough to drive rapid natural selection. The result was evolutionary innovation happening at speeds that were visible within individual lifespans rather than across geological time periods. The implications of this rapid microbial evolution were profound for all larger marine organisms. The base of the marine food web was essentially reinventing itself continuously, creating constantly changing conditions that required corresponding adaptations from every other level of the ecosystem. Marine predators were having to develop increasingly flexible dietary strategies as their traditional prey species evolved new defensive capabilities or shifted to different ecological niches. Some were becoming generalist feeders that could exploit whatever food sources were available, while others were developing highly specialized hunting techniques for capturing specific types of rapidly evolving prey. The most successful marine predators were those that could adapt their hunting strategies as quickly as their prey could evolve defensive responses. This created an evolutionary arms race that was operating at unprecedented speeds, with predator and prey species continuously developing new capabilities in response to each other's innovations. Some marine reptiles were developing what can only be described as learning-based hunting strategies, where individuals could modify their techniques based on experience with different prey types. Some marine predators were becoming incredibly sophisticated, with core behavioral flexibility, was allowing them to remain effective hunters, even as their prey species underwent rapid evolutionary changes. The social hunting strategies detonated group behaviors that could overcome prey defenses that would be effective against individual hunters. These cooperative hunting techniques were requiring enhanced communication and coordination abilities that pushed the cognitive capabilities of marine reptiles to new levels. But perhaps the most remarkable marine innovations were happening among the species that were developing amphibious capabilities, allowing them to exploit resources in both marine and terrestrial environments. These transitional creatures were essentially hedging their evolutionary bets by maintaining access to multiple ecosystems. The physiological challenges of developing truly amphibious capabilities were enormous, requiring simultaneous adaptations for underwater and terrestrial locomotion, respiration systems that could function in both air and water, and sensory systems that could operate effectively in completely different physical environments. Some species were developing sophisticated behavioral strategies that allowed them to optimize their activities for different environments. They might feed primarily in marine environments where food was more abundant, but retreat to terrestrial areas for reproduction or during periods when marine conditions became unfavorable. These amphibious species were becoming living bridges between marine and terrestrial ecosystems, transferring nutrients and energy between environments in ways that were creating entirely new ecological relationships. Their activities were essentially creating hybrid ecosystems that combined characteristics of both marine and terrestrial environments. The success of amphibious species was demonstrating the survival advantages of environmental flexibility during periods of rapid change. Rather than becoming highly specialized for specific conditions, these creatures were developing generalized capabilities that allowed them to thrive across multiple environmental contexts. This evolutionary strategy was proving so successful that it was being adopted by organisms from completely different lineages. The convergent evolution toward amphibious lifestyles was occurring simultaneously among reptiles, early mammals, and even some invertebrate groups, suggesting that environmental flexibility was becoming one of the most important survival strategies. The continental changes that were continuing to reshape the planet were creating new opportunities for amphibious species as coastlines shifted and new water bodies formed. These creatures were often among the first to colonize newly available habitats, giving them access to resources that were unavailable to more specialized species. But let's return our attention to the terrestrial realm, where equally dramatic innovations were occurring among the plant communities that formed the foundation of all land-based ecosystems. The environmental pressures that were challenging animal species were also forcing revolutionary changes in plant evolution that would reshape the entire character of terrestrial environments. The massive coniferous forest that had dominated Mid Jurassic landscapes were beginning to fragment as climate conditions became less suitable for their growth requirements. But rather than simply declining, some plant species were developing remarkable adaptations that allowed them to thrive under the new environmental conditions. Some trees were evolving more efficient water conservation systems that could maintain growth and reproduction even during extended periods of drought. Their root systems were becoming more extensive and sophisticated, developing specialized structures that could extract moisture from soil layers that had previously been unexploitable. The photosynthetic systems of many plants were undergoing fundamental changes that improved their efficiency under varying light and atmospheric conditions. Some species were developing the ability to switch between different photosynthetic pathways depending on environmental conditions, optimizing their energy production for whatever conditions they encountered. But the most revolutionary plant innovations were happening in their reproductive strategies. The environmental instability that was making traditional reproduction unreliable was driving the development of entirely new approaches to ensuring genetic survival across generations. Some plant species were developing incredibly sophisticated seed dispersal mechanisms that could distribute their genetic material across vast distances, ensuring that their offspring would have access to suitable growing conditions, even if local environments became unsuitable. These dispersal systems were often dependent on partnerships with animal species, creating new ecological relationships that benefited both plants and their animal partners. The most innovative plants were beginning to develop what would eventually become the first flowering reproductive systems. While true flowers wouldn't appear for millions of years, the Mid Jurassic Transition Period was witnessing the first experiments in more efficient pollination strategies that would eventually revolutionize plant reproduction. These early flowering mechanisms were often dependent on partnerships with insects, creating mutualistic relationships that provided benefits for both partners while also ensuring more reliable reproduction under changing environmental conditions. The plants provided food rewards for their insect partners, while the insects provided more efficient pollination services than wind-based systems. The development of these plant-insect partnerships was creating feedback loops that were driving rapid evolutionary innovation in both groups. Plants were developing increasingly sophisticated flower-like structures to attract specific insect species, while insects were evolving specialized feeding apparatus and behavioral strategies to exploit these new food sources. The result was an evolutionary arms race between plants and insects that was producing incredible diversity and innovation in both groups. The variety of plant-insect partnerships that were developing was creating new ecological niches and opportunities that hadn't existed during the more stable conditions of the mid-Jurassic peak. Some of the most remarkable plant innovations were happening in response to the changing herbivore communities that were resulting from dinosaur population changes. As some herbivorous dinosaur species declined or shifted their feeding strategies, plants were losing their traditional consumers and having to develop new approaches to seed dispersal and population management. Many plants were evolving enhanced chemical defense systems that could protect them from opportunistic herbivores, while still maintaining partnerships with preferred animal dispersal agents. These chemical systems were incredibly sophisticated, producing different compounds that could selectively attract or repel specific animal species. The chemical ecology that was developing between plants and animals was becoming incredibly complex, with some plants producing dozens of different compounds that could influence animal behavior in precisely controlled ways. These chemical communication systems were essentially allowing plants to manipulate animal behavior to achieve their reproductive and survival goals. But perhaps the most significant plant innovations were happening in their responses to the increasing frequency of catastrophic environmental events. Plants were developing survival strategies that could allow them to persist through major disasters and rapidly recolonize areas after environmental catastrophes. Some species were evolving incredible regenerative capabilities that allowed them to regrow from minimal surviving tissue after fires, floods, or other disasters. Others were developing dormancy systems that could preserve genetic material in suspended animation for extended periods until favorable conditions returned. The seed banks that some plant communities were creating were functioning as biological insurance policies, storing genetic diversity in forms that could survive environmental catastrophes and provide the foundation for ecosystem recovery. When conditions improved, these survival strategies were ensuring that plant communities could maintain continuity even through the most severe environmental disruptions. The success of these plant survival strategies was creating opportunities for rapid ecosystem recovery after catastrophic events. But it was also changing the fundamental character of terrestrial environments. The new plant communities that were emerging from environmental disasters were often quite different from the original ecosystems they replaced. This continuous cycle of destruction and recovery was driving rapid evolutionary innovation as plant species were forced to adapt to constantly changing competitive and environmental conditions. The result was accelerated evolution that was producing new plant species and ecological relationships at unprecedented rates. The changing plant communities were also creating new opportunities and challenges for animal species that depended on vegetation for food and shelter. Some animal species were proving remarkably adaptable to changing plant communities, while others were struggling to adjust to the loss of their preferred food sources and habitat types. The most successful herbivorous species were those that could rapidly learn to exploit new plant resources as they became available. This behavioral flexibility was requiring enhanced cognitive capabilities and more sophisticated digestive systems that could process unfamiliar plant materials. Some herbivorous dinosaurs were developing increasingly generalized digestive systems that could extract nutrition from a wide variety of plant materials, while others were becoming more specialized in exploiting specific plant resources that were becoming more abundant under changing conditions. The predatory species that depended on herbivorous dinosaurs were also having to adapt to changing prey populations and behaviors. Some were developing enhanced hunting strategies that could be effective against prey species that were becoming more cautious and adaptive in response to environmental pressures. The interconnected nature of these ecological changes was creating complex feedback loops where changes in one part of the ecosystem were triggering adaptations throughout the entire community. The result was accelerated evolution across all levels of biological organization, from individual species to entire ecosystems. This period of rapid evolutionary change was testing the limits of biological adaptation and revealing which types of organisms and ecological strategies were most effective for surviving in rapidly changing environments. The lessons learned during this transition would influence the course of evolution for millions of years to come. The organisms that successfully navigated this period of change were those that combined flexibility with efficiency, maintaining the ability to rapidly adapt to new conditions while also developing specialized capabilities that gave them competitive advantages in specific situations. This balance between generalization and specialization was proving to be one of the most important factors determining evolutionary success. As we observe this incredible transformation unfolding across all aspects of the biological world, what becomes clear is that the end of the Mid Jurassic Period wasn't just about the decline of dinosaur dominance. It was about the emergence of entirely new forms of biological organization that would define the future course of evolution. The innovations and adaptations that were developing during this transition period were laying the groundwork for biological capabilities that wouldn't be fully realized for millions of years. The cognitive advances, metabolic innovations, and ecological strategies that were emerging would eventually lead to forms of life that would exceed even the remarkable achievements of mid-Jurassic evolution. The story that was unfolding was not one of decline and extinction, but of transformation and renewal. The biological world was reinventing itself in response to changing conditions, developing new solutions to survival challenges that would prove even more sophisticated and successful than what had come before. But here's where the story takes an absolutely mind-blowing turn that reveals just how interconnected these evolutionary innovations really were. The changes happening in marine environments weren't occurring in isolation from terrestrial developments. Instead, they were part of a planet-wide biological revolution that was creating feedback loops between land and sea that would reshape the entire biosphere. The coastal regions where marine and terrestrial environments met were becoming laboratories for some of the most extraordinary evolutionary experiments in Earth's history. These transition zones were experiencing environmental conditions that were completely unprecedented, creating opportunities for organisms that could exploit resources from both land and sea simultaneously. Some of the most remarkable adaptations were happening among creatures that were essentially inventing amphibious lifestyles from scratch. These weren't just animals that could survive in both environments. They were developing integrated physiological systems that could optimize performance for completely different physical challenges within the same organism. Consider the respiratory innovations that were required for true amphibious capability. These animals were evolving dual respiratory systems that could extract oxygen efficiently from both air and water, switching between completely different breathing mechanisms depending on their current environment. Some species were developing specialized lung structures that could collapse and expand to accommodate the pressure changes involved in diving, while maintaining the surface area necessary for efficient gas exchange in air. The circulatory modifications required to support amphibious lifestyles were equally impressive. These creatures needed cardiovascular systems that could function optimally whether they were swimming against water resistance or moving across land. Their hearts were evolving variable pumping capabilities that could adjust blood pressure and circulation patterns in real time based on activity requirements. But perhaps the most fascinating amphibious innovations were happening in sensory systems that had to function effectively in completely different physical media. Water and air transmit sound, light, and chemical signals in fundamentally different ways, requiring sensory apparatus that could recalibrate automatically as animals move between environments. Some amphibious species were developing acoustic systems that could function as both underwater sonar and aerial hearing, switching between different frequency ranges and processing algorithms depending on the medium they were operating in. Their brains were evolving specialized neural circuits that could interpret the same sensory input differently based on environmental context. The chemical sensing capabilities of these creatures were becoming incredibly sophisticated, with specialized organs that could detect both waterborne and airborne chemical signals. This dual chemical sensing was allowing them to track prey, identify predators, and locate resources across environmental boundaries that would be impossible for purely terrestrial or aquatic species to cross. These sensory innovations were creating new possibilities for long-distance navigation and communication that could operate across multiple environments simultaneously. Some amphibious species were developing migration strategies that use landmarks from both terrestrial and marine environments, creating navigation systems of unprecedented accuracy and reliability. The behavioral implications of these amphibious capabilities were staggering. These creatures could escape terrestrial predators by diving into water bodies, then evade aquatic threats by moving onto land. This escape flexibility was providing survival advantages that were impossible for species restricted to single environments. But the most significant impact of amphibious evolution was on ecosystem connectivity. These creatures were serving as biological bridges that transferred nutrients, energy, and genetic material between marine and terrestrial environments in ways that were creating entirely new ecological relationships. When amphibious animals fed in marine environments and then moved to terrestrial areas, they were essentially pumping ocean-derived nutrients into land-based ecosystems. Conversely, when they fed on land and returned to water bodies, they were transferring terrestrial resources to aquatic communities. This cross-ecosystem nutrient transfer was dramatically increasing the productivity of both environments. The reproductive strategies of amphibious species were equally revolutionary. Some were developing breeding systems that took advantage of resources from both environments, using marine areas for feeding and growth, while utilizing terrestrial sites for reproduction and offspring care. This environmental partitioning was allowing them to optimize different life stages for different ecological conditions. Other amphibious species were experimenting with reproductive strategies that actually required both environments for successful completion. Their eggs might need terrestrial conditions for initial development, but aquatic environments for hatching and early growth. These complex life cycles were creating dependencies on environmental stability across multiple ecosystems simultaneously. The success of amphibious lifestyles was inspiring similar evolutionary experiments among organisms from completely different lineages. Plants were beginning to develop amphibious capabilities that allowed them to colonize shoreline environments that experienced regular flooding and drying cycles. These amphibious plants were evolving root systems that could function both as terrestrial anchoring and nutrient absorption mechanisms and as aquatic filtering and gas exchange organs. Their leaves were developing waxy coatings that could repel water when necessary, while also being permeable enough to allow underwater photosynthesis during flooded periods. Some plant species were taking amphibious adaptation even further, developing the ability to change their entire growth form depending on whether they were in terrestrial or aquatic conditions. The same plant could produce terrestrial leaves optimized for air-based photosynthesis and aquatic leaves specialized for underwater conditions. These morphological flexibility capabilities were requiring incredibly sophisticated genetic control systems that could coordinate completely different developmental programs within the same organism. The plants were essentially maintaining multiple biological identities that could be activated depending on environmental conditions. The ecological implications of amphibious plant evolution were enormous. These species were creating habitat continuity across environmental boundaries that was supporting much more diverse biological communities than would be possible with purely terrestrial or aquatic vegetation. Amphibious plant communities were also serving as biological filters that could process nutrients and pollutants from both terrestrial runoff and aquatic systems, creating cleaner and more stable environmental conditions for other organisms. Their root systems were functioning as living water treatment facilities that maintained water quality across entire watersheds. But let's shift our focus to another group of organisms that were developing equally remarkable innovations during this period of environmental transition. The flying insects were experiencing an evolutionary explosion that was creating aerial ecosystems of incredible complexity and sophistication. The environmental instability that was challenging larger organisms was actually creating opportunities for insects that had the mobility to rapidly exploit new resources as they became available. Their ability to fly between different habitat patches was allowing them to survive environmental changes that were devastating to less mobile species. But the insects weren't just surviving the environmental transitions. They were thriving and diversifying at rates that exceeded anything seen in other organism groups. The fragmentation of stable ecosystems was creating thousands of new ecological niches that insects were rapidly evolving to exploit. Some insect species were developing incredibly specialized feeding strategies that allowed them to exploit resources that were inaccessible to other organisms. They were evolving mouth parts that could pierce the tough outer layers of seeds that had developed enhanced protective coatings, or specialized digestive systems that could process plant materials that had evolved new chemical defenses. The most remarkable insect innovations were happening in their social behaviors. Some species were developing cooperative strategies that allowed them to tackle resource extraction and processing tasks that would be impossible for individual insects to accomplish. These early social insects weren't just working together randomly. They were developing sophisticated division of labor systems, where different individuals specialized in specific tasks like food collection, nest construction, defense, and care of developing young. The efficiency gains from this specialization were allowing insect colonies to exploit resources far more effectively than solitary species. The communication systems that social insects were developing were becoming incredibly sophisticated. They were evolving chemical signaling capabilities that could convey detailed information about resource locations, environmental threats, and colony needs across distances and through complex three-dimensional environments. Some social insect species were developing what can only be described as primitive agricultural systems, cultivating fungi or other organisms that could process organic materials into more digestible forms. These farming insects were essentially creating controlled ecosystems within their colonies that could produce food resources more reliably than foraging in unpredictable external environments. The architectural capabilities of social insects were equally impressive. They were constructing nest systems with sophisticated climate control, ventilation, and structural engineering that could maintain optimal conditions for colony survival, regardless of external environmental fluctuations. These insect colonies were becoming so sophisticated in their organization and capabilities that they were functioning almost like multicellular organisms, with individual insects serving specialized roles similar to different organ systems in larger animals. The collective intelligence and problem-solving capabilities of these colonies were exceeding what individual insects could achieve by enormous margins. But perhaps the most significant impact of insect diversification was on the pollination systems that were becoming crucial for plant reproduction. As environmental changes disrupted traditional wind-based pollination, plants were increasingly dependent on insect partners for successful reproduction. This dependency was driving rapid coevolution between plants and insects that was producing remarkable innovations in both groups. Plants were developing increasingly sophisticated flower-like structures designed to attract specific insect species, while insects were evolving specialized feeding apparatus and behaviors that made them more effective pollinators. The diversity of plant-insect partnerships that were emerging was staggering. Different plant species were developing relationships with different insect groups, creating complex networks of mutual dependency that were stabilizing both plant and insect populations during periods of environmental uncertainty. Some of the most remarkable plant-insect relationships were developing between species that provided multiple services for each other beyond simple pollination. Plants might provide food, shelter, and protection for their insect partners, while insects provided pollination, seed dispersal, and defense against herbivorous animals. These mutualistic relationships were becoming so sophisticated that some plant and insect species were evolving in perfect synchronization, with their life cycles precisely coordinated to maximize mutual benefits. The timing of plant flowering, insect emergence, and reproductive activities was becoming incredibly precise, creating biological partnerships that functioned like perfectly synchronized machines. The success of these plant-insect partnerships was creating new opportunities for other organisms that could exploit the resources and services provided by these relationships. Some animals were learning to take advantage of the predictable food sources created by plant-insect partnerships, while others were developing strategies for intercepting the resources being transferred between plants and their insect partners. This was creating increasingly complex ecological networks where the success of individual species was dependent on the health and stability of multiple partnership relationships. The interconnectedness of these biological communities was providing resilience against environmental changes, while also creating vulnerabilities that could cascade through entire ecosystems if key partnerships were disrupted. The rapid evolution of these complex ecological relationships was requiring enhanced cognitive capabilities across many different organism groups. Animals that participated in multiple ecological partnerships needed sophisticated behavioral strategies that could optimize their interactions with different species while also responding to changing environmental conditions. Some species were developing what can only be described as ecological intelligence, with enhanced abilities to understand and predict the behaviors of other species in their community. This ecological intelligence was allowing them to anticipate changes in resource availability, predict the activities of potential competitors or partners, and optimize their own behaviors for maximum ecological success. The development of ecological intelligence was particularly evident among the predatory species that needed to understand the complex relationships between their prey species and other members of their ecological community. Successful predators were learning to exploit the ecological dependencies of their prey, using knowledge of their prey's partnerships and resource requirements to improve hunting success. Some predators were developing hunting strategies that specifically targeted the ecological relationships that their prey depended upon, disrupting partnerships or resource flows in ways that made their prey more vulnerable to predation. This ecological manipulation was requiring unprecedented levels of behavioral sophistication and environmental understanding. The arms race between predators developing ecological manipulation strategies and prey species evolving counter strategies was driving rapid innovation in behavioral complexity across entire ecosystems. The result was biological communities where every species was constantly adapting not just to environmental conditions, but to the evolving strategies of multiple other species in their community. This dynamic ecological environment was creating selection pressures that favored intelligence, behavioral flexibility, and rapid learning capabilities across many different organism groups. The creatures that were most successful were those that could quickly understand and adapt to changing ecological relationships within their communities. The cognitive evolution that was occurring during this period was laying the groundwork for intelligence capabilities that would eventually exceed anything seen during the stable period of Mid Jurassic dominance. The environmental challenges and ecological complexity were driving brain evolution at unprecedented rates across multiple lineages simultaneously. Some of the most remarkable cognitive innovations were happening among species that were developing enhanced social intelligence. The complex partnerships and cooperative relationships that were becoming essential for survival were requiring sophisticated abilities to understand and predict the behaviors of other individuals within social groups. These social intelligence capabilities were enabling the development of cultural transmission systems, where learner behaviors and successful strategies could be passed between individuals and across generations much more rapidly than genetic evolution alone could accomplish. Some species were essentially developing primitive educational systems where experienced individuals taught essential skills to younger community members. The cultural evolution that was beginning to emerge was creating feedback loops with genetic evolution that were accelerating the pace of adaptation beyond what either process could achieve independently. Learned behaviors that proved successful were creating selection pressures that favored genetic changes supporting those behaviors, while genetic innovations were creating new capabilities that could be enhanced through learning and cultural transmission. This interaction between genetic and cultural evolution was producing adaptive capabilities that were far more sophisticated and flexible than anything that had existed during previous periods of Earth's history. The organisms that were mastering this dual evolutionary strategy were developing problem-solving abilities that could address novel challenges in real time rather than waiting for genetic adaptations to develop over multiple generations. The implications of these cognitive and cultural innovations extended far beyond individual survival. Species that developed sophisticated learning and cultural transmission capabilities were becoming ecosystem engineers that could actively modify their environments to create more favorable conditions for their communities. Some species were developing landscape management strategies that involved coordinated activities across multiple individuals and even multiple generations to create and maintain optimal habitat conditions. These ecosystem engineering projects were requiring long-term planning abilities and cooperative capabilities that represented entirely new forms of biological organization. The success of these ecosystem engineering strategies was creating environmental stability that benefited not only the species that initiated the projects, but entire biological communities that shared their habitats. The most sophisticated ecosystem engineers were essentially creating biological civilizations that could maintain favorable conditions even during periods of environmental instability. But perhaps the most remarkable aspect of this period of biological innovation was how quickly these new capabilities were spreading between different lineages and geographic regions. The environmental pressures that were driving innovation were creating similar challenges for organisms around the world, leading to convergent evolution of similar solutions across multiple independent lineages. The speed at which successful innovations were spreading suggests that organisms were developing increasingly sophisticated methods for observing and learning from the successful strategies of other species. Some species were apparently capable of adopting and modifying successful behaviors that they observed in completely different types of organisms. This cross-species learning was accelerating the pace of innovation beyond what any single lineage could achieve through independent evolution. The biological world was essentially functioning as a massive research and development system where successful innovations could be rapidly tested, modified, and adopted across multiple species and ecosystems simultaneously. The result was an explosion of biological innovation that was producing new capabilities and ecological strategies at unprecedented rates. The diversity of solutions being developed to address environmental challenges was creating a biological toolkit that would provide the foundation for even more sophisticated innovations in future evolutionary periods. The organisms that were emerging from this period of intense innovation were fundamentally different from their mid-Jurassic ancestors, not just in their physical characteristics, but in their cognitive capabilities, social organizations, and ecological strategies. They represented entirely new forms of biological organization that would define the future course of evolution for millions of years to come. As we witness this incredible transformation reaching its crescendo, what becomes clear is that the end of the Mid-Jurassic Period wasn't marking the conclusion of biological innovation, but rather the beginning of an even more sophisticated phase of evolutionary development. The challenges that had initially seemed like threats to biological diversity were actually catalyzing innovations that would lead to forms of life far more complex and capable than anything that had existed before. The stage was being set for biological communities that would combine the best innovations from this period of transition with new capabilities that were still emerging from the ongoing evolutionary experimentation. The future would bring forms of life that would make even the remarkable achievements of the Mid-Jurassic Period seem like preliminary experiments in the vast potential of biological evolution. But the most extraordinary development happening during this transition wasn't visible to the naked eye. Deep within the cellular machinery of countless organisms, a revolutionary process was unfolding that would fundamentally change how life itself operated on our planet. The microscopic engines that powered every living cell were undergoing modifications so profound that they were essentially rewriting the rules of biological existence. The mitochondria within animal cells were evolving enhanced efficiency systems that could extract far more energy from the same amount of food resources. These cellular powerhouses were developing new metabolic pathways that could switch between different fuel sources depending on availability, creating biological engines that could run on whatever energy sources were accessible in increasingly unpredictable environments. Some organisms were developing mitochondrial systems so efficient that they could maintain active lifestyles on drastically reduced food intake, while others were evolving the ability to enter suspended animation states, where cellular processes could be slowed to nearly zero during periods of extreme resource scarcity. These cellular innovations were providing survival capabilities that exceeded anything possible through behavioral adaptations alone. The most remarkable cellular developments were happening in the DNA repair and replication systems that maintained genetic information across generations. The environmental stresses that were challenging organisms were also creating increased rates of genetic damage that could prove fatal if not properly managed. Evolution was responding by developing increasingly sophisticated molecular machinery that could detect and repair genetic damage with unprecedented accuracy. These enhanced DNA repair systems weren't just preventing genetic deterioration, they were also enabling more rapid evolutionary adaptation. by allowing organisms to survive higher rates of genetic variation while maintaining essential cellular functions. The result was accelerated evolution that could produce significant adaptive changes within just a few generations, rather than the thousands of generations typically required. Some organisms were developing what can only be described as genetic editing systems that could make precise modifications to their own DNA in response to environmental pressures. This capability was allowing them to adapt to changing conditions in real time, essentially becoming their own genetic engineers. The implications of this self-directed evolution were staggering, as it meant that organisms could actively participate in their own evolutionary development. But perhaps the most mind-blowing cellular innovation was the development of enhanced cellular communication systems that allowed individual cells within multicellular organisms to coordinate their activities with unprecedented precision. These intercellular communication networks were becoming so sophisticated that they could coordinate complex responses across entire organisms within minutes of detecting environmental changes. The immune systems of many organisms were undergoing equally dramatic improvements, developing the ability to rapidly identify and respond to new types of threats that had never been encountered before. These enhanced immune capabilities weren't just defensive. They were also enabling organisms to form beneficial partnerships with microorganisms that could provide essential services like nutrition processing and toxin neutralization. Some organisms were essentially cultivating internal ecosystems of beneficial microorganisms that functioned as external organs, providing capabilities that would have been impossible to develop through their own genetic evolution alone. These internal partnerships were creating biological systems that combined the capabilities of multiple different types of organisms into integrated wholes that exceeded the sum of their parts. The complexity of these internal ecosystems was requiring sophisticated management systems that could maintain optimal balances between different microbial communities while also responding to changing external conditions. Some organisms were developing what amounted to internal environmental control systems that could regulate the conditions within their bodies as precisely as they regulated their external behaviors. These internal ecosystem management capabilities were particularly crucial for the largest organisms, whose size created unique challenges for maintaining physiological stability across their entire body mass. The massive sauropods that were still surviving were developing internal circulation and regulatory systems that could maintain optimal conditions from their heads to their tails, despite the enormous distances involved. The engineering challenges involved in maintaining circulation and nervous system function across such enormous bodies were requiring biological solutions that pushed the boundaries of what seemed physically possible. Some species were developing auxiliary circulatory systems that could maintain blood flow to extremities that would otherwise go beyond the reach of their primary cardiovascular system. The nervous systems of these giant creatures were evolving increasingly sophisticated signal processing capabilities that could coordinate complex behaviors across body systems that spanned dozens of meters. The neural innovations required to maintain conscious control over such enormous bodies were creating brain structures and processing capabilities that exceeded anything seen in smaller animals. But the most fascinating aspect of giant animal physiology was how they were solving the communication challenges involved in coordinating activities between body parts that might be separated by enormous distances. Some species were developing internal communication systems that functioned almost like biological telegraph networks, allowing rapid signal transmission across their entire body length. These internal communication innovations were enabling behavioral capabilities that would have been impossible without sophisticated coordination between widely separated body parts. Giant herbivores could simultaneously monitor their environment for threats while coordinating complex feeding behaviors that involved precise positioning of their massive heads and necks. The predatory giants were developing even more sophisticated internal coordination systems that could integrate sensory information from across their entire body, while coordinating complex hunting behaviors that required split-second timing and incredible precision. Their ability to coordinate attacks involving their entire body mass was creating hunting capabilities that were devastating to their prey. But as remarkable as these individual innovations were, the most significant developments were happening in the interactions between different species that were creating entirely new forms of biological organization. The environmental pressures that were challenging individual organisms were also creating opportunities for cooperative relationships that could provide survival advantages that neither species could achieve independently. Some of the most extraordinary partnerships were forming between species that had previously been competitors or had no interaction at all. Environmental changes were creating situations where cooperation provided such significant advantages that traditional competitive relationships were being replaced by mutualistic partnerships almost overnight in evolutionary terms. The most successful of these new partnerships were those that combined complementary capabilities from different species in ways that created emergent properties that exceeded what either partner could accomplish alone. Some plant-animal partnerships were creating integrated systems where the plant provided energy and resources, while the animal provided mobility and environmental manipulation capabilities. These integrated partnerships were essentially creating new types of organisms that combined the best characteristics of both partners while minimizing their individual limitations. The resulting biological systems were proving far more adaptable and resilient than either species could be independently, creating survival advantages that were crucial during periods of environmental instability. But the most remarkable aspect of these partnerships was how quickly they were evolving from simple resource exchanges to sophisticated integrated relationships that required complex coordination and communication between very different types of organisms. Some partnerships were developing communication protocols that allowed species with completely different sensory and cognitive systems to share detailed information about environmental conditions and resource opportunities. The development of cross-species communication was creating biological communities that functioned almost like distributed intelligence networks, where the cognitive capabilities of multiple different species could be combined to solve problems that would be impossible for any individual species to address. These collective intelligence systems were producing problem-solving capabilities that exceeded anything seen in individual organisms. Some biological communities were developing what can only be described as distributed decision-making systems, where complex choices about resource allocation, territory management, and response to environmental threats were made through collective processes involving multiple species. These community-level decision-making capabilities were creating adaptive responses that were far more sophisticated than individual species could develop independently. So there you have it. The most unusual dinosaurs of the Mid Jurassic Period weren't just bigger versions of familiar creatures. They were evolutionary masterpieces that pushed the boundaries of what seemed possible in the natural world. From the impossibly long-necked giants that could peer into treetops like living skyscrapers, to the precision-engineered predators that dominated their ancient landscapes, every single adaptation told a story of innovation under pressure. These remarkable creatures had solved survival challenges in ways that still leave modern scientists amazed, creating a biological civilization so sophisticated it managed Earth's climate and ecosystems for millions of years. Their legacy lives on in the evolutionary innovations they pioneered, innovations that would eventually give rise to the incredible diversity of life we see today.